right, hello. How you guys doing? Doing all right? You'll have probably noticed I posted midterm grades, and basically what I did, just so you know, is I came up with an approximate average as if like what grades we have so far are all the ones that will exist. But that's not a very accurate representation because I take the average of, of exam 1 plus exam 2 plus the final exam, averaging those three categories with the combination of your participation and homework grades, and that gets your total grade. But we've only had one exam, so the weighting is effectively different than what it will be at the end of the semester. So just keep in mind that even though I'm calculating it that way to give you a midterm report, it'll look different as we get the other exams as well. But that's there. You can get an idea of approximately the participation outcome kind of situation. You'll notice that if you've been involved in participating in all the different assignments, it should be a pretty good score. And I think that the minimum grade I gave for any assignment, like quiz type thing that you participated in, was an 80, I think. So like if you got everything wrong on the crypto quiz or something, your overall score for that moment came out as an 80. One thing I will also note is I tend to, just in case I don't give you enough participation activities, if I feel like I've shortchanged you, then I will just default to giving you full credit for times where I didn't take it up to maybe about 10 scores total. So if we get 6 or 7 scores, that'll give me some good idea of who's participating, who's doing stuff. There'll be enough challenge in there to be like, oh, I want to do well on this participation score, but it's kind of low key, right? So that's my thinking. Trying to get your engagement in that manner. Okay, and so I know at minimum we'll do a Flint water crisis one as well. So you'll probably expect 2 to 3 more participation quizzes. I'll try to get more than that, just to add. But okay, so at any rate, today, so we finished membranes last time. Today we'll start talking about disinfection, and I will work to get post a homework probably today or tomorrow for you, and that'll be due the day of our exam review. So disinfection is a fun one. That's kind of my expertise if I were to just select one category here. So today we'll have some, I hope, interesting discussions. And we'll start by describing, okay, is it disinfected or is it sterile? How many of you would feel like you knew the difference before looking at like the little bullet points here? Anyone feel like you knew the difference between some water or food being sterile versus disinfected? Okay, so how many of you would think that my bottle of water would have any bacteria or viruses alive inside of it? If let's say okay, so some hands are already raising up, right? So I probably just drank out of it, right? So what if I cleaned it really well first, there's nothing in it, and then I poured water in it from one of the water bottle dispenser taps in PFT? How many of you think there would be some viruses or bacteria in there? Okay, some. How many think none? Okay, nobody's like confident enough to say, no, there should be none. Okay, how many think there should be none? Okay, so some of you thinking that there should be none ideally. How many of you are just not going to answer? Oh, looks like everybody, right? Okay. All right, so the difference here is sterile can kind of mean a couple different things. You may recognize it from when we talk about animals. We will sterilize. You'll hear sterilize like we sterilize some surface, but you could also talk about an animal being sterile, whether it's maybe like a mule that's a hybrid breed that's not capable of reproducing, or you could say technically when you spay or neuter your cat or dog, you're sterilizing it. It is now sterile, meaning it cannot reproduce. So one of the definitions is things that can't reproduce. So if we were to cause a bacteria to have some DNA damage such that it could no longer reproduce, but it was still alive for the moment, that would technically be sterile in that sense. Generally, if we're talking about like laboratory stuff or dealing with food or water, and we're talking about sterile or medical stuff, usually we're meaning we just absolutely destroyed it completely. But effectively, in terms of like infections and things like that, if you just prevent anything from reproducing, then you cannot get an infection, because an infection is literally the scenario when this microbe reproduces a whole lot. It's taking your resources in your body and reproducing, whether that's infecting your cells as a virus, making more viruses, and all that. In some way or another, that infection relies on that reproduction. Okay, so then disinfected is a bit of a different term, where we would say we don't actually have to destroy everything. We just have to reduce the infectious stuff, the stuff that could make you sick, to levels where it won't make you sick. Okay, so it's removal or inactivation of pathogenic microbes at infectious levels. So when I drink from my bottle of water here, I can guarantee you that I'm drinking thousands, if not millions, of microorganisms. And that's okay. I'm all right with that. In part because it's been a while since I've like thoroughly cleaned it, but in part because there's just some stuff in there. There's going to be some viruses, probably some viruses that infect algae, for example, or infect some bacteria that are just in there. Some of them survive the water treatment system and make their way through, or maybe there's some bacteria growing on some of the pipes. The point is, though, that they should not be infective, especially not at infectious levels. Now, if I were to tell you that had I intentionally added some pathogenic Vibrio cholera that gives the dreaded cholera disease, right? If I were to know that I could add exactly 10,000 cholera bacteria to my liter of water here, I could actually still drink that and be pretty confident that I'll be okay. It turns out that it takes a lot of cholera to get somebody sick. Now, if it was 10,000, I might hesitate. If it was 1,000 or 100, I would probably actually be like, oh, that's kind of neat. Let's do this just to prove the point, right? Maybe it's not a great idea, but as we'll talk about in a couple minutes, we actually have some pretty good info on how that works and what our body can do to protect ourselves. Okay, so in the scheme of things, we've looked at this a few times. Our disinfection is really kind of the final step. Maybe we'll do some sort of polishing, maybe adjust for corrosion control, maybe add fluoride. But generally, by the time we're disinfecting, we've cleaned up the water quite a bit. And so here we see in this diagram, we're essentially running it through a plug flow reactor type of a treatment in order to reduce the number of pathogenic organisms way down to a small number. And if you recall, the difference between a CSTR that's completely well mixed and the plug flow reactor as drawn there, the plug flow reactor does a better job of getting it to a very low level. And that's because that plug that's flowing through is not mixing with what's at the end, right? So with the same volume of a container, our plug flow reactor will be much more efficient at getting like the 99.99% reduction that we might be after. That's one way to think about that, is because at the start of a CSTR, part of that gets diluted into the bigger volume is immediately mixed. Even though you're killing stuff in there, part of what you just added is immediately mixed with what's leaving the reactor. And so you just need a really much larger container to get a big dilution to happen when you mix it like that. Okay, so plug flow reactor is typically what we're going to use. So let's talk about our targets here. There's a few different types of organisms that we could consider that would be important to destroy or remove. First would be viruses. Heard a lot about those over the past few years. Noroviruses are a common one, and a lot of these will be food or waterborne. We're specifically looking at waterborne, but a fair amount of the knowledge that we have comes from like foodborne outbreaks. And, okay, how do we prevent those? Who done it at, Chipotle or wherever? And for the most part, these are in some manner scenarios when if somebody's infected, then the barriers to the fecal-oral route of transmission have broken down, right? That's the issue. So when we want to make sure that barrier doesn't break down in water treatment, we need to make sure, okay, we're capable of removing this type of virus to a level where it's no longer infectious. So the dose makes the poison. So how much of a particular virus does it take to get somebody sick? Because that's kind of our design criteria. We need to get below that. Well, it turns out norovirus, which is not such a fun bug to get. That's the kind where you might get a food infection about 8 to 12 hours after eating some food that perhaps somebody did not have proper hygiene when they were preparing that food, and so then you're sick, right? And then it's a very, very bad night, and you probably feel awful the next day, and then you're pretty much better after that. So that would be pretty typical for what we would call, most people would say food poisoning, but technically that would be a food infection. Food poisoning is if there's happens to be a poison that maybe a microbe or maybe some other way that a poisonous substance got into the food. That's usually a pretty immediate reaction. It's like a minute later you're in a bad spot. Generically, we often call both food poisoning just because that's kind of colloquial, how people refer to it. So noroviruses, for example, it takes something like, I think it was 10 to 50, maybe even a little bit less, viruses to cause an infection. Something on that order, and I need to dig up my old notes to get the exact, but it's not very many. It's a few of these viruses can get you sick. It takes a few hours for them to actually find a host to start infecting the cells, to create a lot of them, which then your body responds to in uncomfortable ways. Okay, so that's pretty similar to rotaviruses, polioviruses as well. These are all viruses that, it's a fecal-oral route. I don't recall exactly the number of polioviruses, but as we start thinking about this, we recognize, okay, if we just ingest a few to maybe tens of these, we may have a problem. So then we might want to think about the fact that, well, how many might be in our water supply? Now, hopefully it's not as bad as the case we'll look at with we'll talk about in a few minutes with the ghost map. So perhaps if we're taking from a river, maybe we should just assume there's 100 per liter or something like that. And so then when we design our criteria, we'll say, all right, well, we need to make sure that for any given virus, we're reducing it by 99.9%, because nobody's going to drink 100 liters. So nobody's going to get that dose that could get them sick under circumstances that are anywhere near normal with what we might expect in our influence. Okay, so that's kind of one key aspect there. So I mentioned Vibrio cholera. It turns out that this takes something like 10 to the 6, so 1 million to 10 million of these cholera cells, Vibrio cells, in order to actually give somebody an infection. Now, the reason for that is because they are very sensitive to acidity. So if you have good stomach acid, then that alone will kill off so many of them that they're not likely to give you an infection. And if you look at the 10 to the 6 or 10 to the 7th, maybe just your stomach acid alone is killing 10 to the 5th of them, like 99.999%, right? And so if you're killing that many of them, there has to be more than that amount to get you sick. Now, here's a little life hack for you. One of the reasons why it's, you know, a little bit of a gamble to eat raw oysters is because raw oysters are very good at filtering out small things like bacteria and viruses, like noroviruses, Vibrio cholera. And a lot of the Vibrio species are actually just native to saltwater systems. So whether it's wastewater that might flow over an oyster bed or some just natural occurrence, there is potential for them to filter out and grab a bunch of pathogens so that when you eat it raw, having not cooked those pathogens, you may be in some trouble. So the life hack would be, I don't tend to eat raw oysters myself, but if I was going to, I'd make sure I would do it on an empty stomach. So my stomach acid would be in full force to do a little bit of cooking or microbial inactivation. So would actually make a lot of sense to eat raw oysters as an appetizer instead of as a dessert, right? So that's my recommendation to you. For E. coli, typically it's something like 10 to the fourth, so maybe 10,000 or so. Same with salmonella. Both E. coli and salmonella can create toxins. So they could, if you had some canned food that was sitting there but it was not properly canned and there was some microbe, here's where you'd get food poisoning. If something was producing the toxin right there, then you eat it and immediately have an issue. That would be a bacteria-related food poisoning. So some of them are just simply pathogenic and give you a problem with the infection. Some of them will give you a problem with that infection plus produce a toxin and then give you a problem. But a lot of this is actually about where in your stomach system it is, because we actually probably all have E. coli in our guts, but it's in the right spot, right? We don't want it in the wrong spot where it could grow and cause problems, giving us an illness, right? So some of this is just about, hey, where is it, and can our bodies control for that properly? One thing that kind of ties those two thoughts together, if you've ever heard about it, you're not supposed to feed honey to infants, and the reason is because infants don't have a well-developed stomach yet, so they don't have the stomach acidity to deal with something that commonly occurs in honey, which is the botulinum bacteria. So botulinum subtilis, maybe. The bacteria that produces botulism toxins, or that could cause botulism, is actually relatively common in honey. Now, it can't produce the toxin in the honey because it can't really grow there, but it can be there as like a little spore or a cyst. It can just kind of close itself off and it's just sitting there. Then if it gets to a proper environment, for example, like a scenario where it gets past the stomach acidity into maybe it's the duodenum, whatever's next. In infants, the acidity is not strong enough to kill them, and so if the botulinum bacteria grows, and it produces the toxin, that will be lethal for the child. So we're actually like, that's one of the concerns there. Whereas any adult human will be protected from that just simply because the stomach acidity there. So last category would be protozoa. These are a lot like bacteria, but instead of having, if you think way back to biology, you learned that some things have a cell wall, some things have a cell membrane, and there's some difference, right? The prokaryotic, eukaryotic. Bacteria are prokaryotic. We're prokaryotes. That just means they have a lipid membrane. So lipid is kind of like fatty type molecules, and they're all arranged in these phospholipid things. Well, these guys are eukaryotic, meaning they have full cell walls. They're just more robust, more protected from the environment. They tend to be larger. They tend not to grow quite as rapidly. So, you can have amoebas that can be a problem, and then two species that we would generally call like just generically parasites. I mean, there's all sorts of parasites, they don't have to be single cellular, but for single cellular parasites, Cryptosporidium parvum and Giardia, several species, would be what we think of. And these would be, you read the paper on Cryptosporidium, big, massive outbreak. It turns out it doesn't take very many of these at all to get somebody sick. It's something like between 1 to 5 cells. These are also what you might consider hiker's diarrhea or something if you were out in nature and you drank some water that maybe you should have purified better. They can be pretty resistant in the environment if they close up to form a protective cyst. Then they're pretty resistant to chlorine, for example. So when we consider chlorine dosing, we need to make sure we get rid of pretty much all of those, or nearly so, in order to protect human health. As you read in that article on Cryptosporidium, it turns out that it's a big problem for anybody that's immunocompromised. So, you might think, oh, haha, a lot of people, this entire city had diarrhea. That's like almost funny, but it's it actually also caused a lot of deaths. So that not quite funny in that sense. If not for that, maybe it would just be an embarrassment, right? And like, oh yeah, let's not do that again. But it's actually can be a really, really big issue for immunocompromised people because it's a tough bug for your body to deal with, and we don't have great protections against eukaryotic infections. Okay, so with all of that, there's an elephant in the room. How do we know how many cells it takes, how many viruses it takes? Any ideas how we might measure that? Rats? Okay. That's a good idea, and ideally we would do that, but some of these are non-pathogenic to other organisms, right? So exactly. Couldn't have said it better myself. So funny enough, what the CDC has done on several occasions is probably reaching out to a lot of college students and so on, and be like, hey, who wants $1,000? You'll get an all expenses paid stay in our little hotel hospital thing for a week. All your food will be very well controlled and clean, and we'll make sure we know exactly what you've eaten and drank, and that'll all be included. You'll have Wi-Fi and a nice restroom that you might need, and we're just going to ask you that you take this little pill. If you're lucky, it's going to be placebo. It'll just be a little sugar. It'll just hang out for the week. If alternatively, you might get lucky and it's a really small dose, and that just doesn't have to be infective, but we need that data. Or you might get that capsule that has tons and tons of these viruses. And so we're just paying you to have a bad time, but get paid for it, right? So couldn't have said it better myself. So how many of you think you'd maybe volunteer for that? Nobody? What's that? A lot more than 1,000. Yep. So it's presumably they'd have all the care on site, so you wouldn't die or anything. But yeah, hopefully, right? Somebody would be in big trouble if that got to that point, right? So pretty funny. Maybe and I learned about that probably 10 years ago now. So maybe in today's dollars it would be a little more than that, but yeah, would be quite the interesting gamble, I think. How many of you have had some sort of food infection within the past few years? It's no fun, right? So definitely, if you had anything like that recently, it'd be pretty hard to say yes to that, I think. Okay, so let's talk about the father of epidemiology, the guy who first discovered waterborne diseases in some way. Turns out his name was Jon Snow, not the Game of Thrones guy, and unfortunately not necessarily related to me because he had no children, but perhaps tangentially related. I don't know. So the English doctor in the 1850s. By the way, I do have a brother named John, so he knows nothing. If you're familiar with Game of Thrones. But Jon Snow, the doctor guy, was really responsible for kind of the first observations or first mapping of disease, and using a disease map to really identify where is this coming from, what's the problem, and how do we deal with it. So if you think back to the 1850s, this was kind of just around the time where we were starting to develop a germ theory of disease, probably a little bit before. And so if you consider any sort of a epidemic of disease, that's got to be terrifying, right? Because you don't know what causes it. You have all these superstitions. You're trying to deal with it, and people are dying all around you. So what do you do, right? That's pretty terrifying. So there was a case we're going to talk about in London that centered around the Broad Street pump. It was a well in a particular location. And this was really that kind of the first documentation of germ theory of disease, kind of showing what was going on. So there's a great book. It's an easy read that is kind of an illustration of the historical events. The text itself, a lot of it is just simply factual, but they tell it in story form, adding some fictional details to make it flow like an actual novel kind of thing. Even though we don't know that, John just said XYZ to so-and-so, even though we don't know that exact phrase happened, they filled it in fictitiously, following the historical details as best they could. So it's not a fiction necessarily. It's like, as historical as possible, but fictionalized to tell the story. So that's this book here. So definitely recommend that if you're at all interested. And if you do much with public health or epidemiology ever, you'll definitely come across a lot of people who know about this book. So here's the ghost map. I have another image that shows it a little better or highlights it a little better. But if you look, it just kind of looks like a map at first. And then if you look closely, each of these black bars represents someone who died of cholera during this outbreak. And so you'll notice that some of these households have very large bars there, meaning there was lots and lots of people who died in that house. So cholera, I talked about it earlier. I made the joke that if I had, X number of bacteria, Vibrio cholera in here, maybe I'd drink that on an empty stomach and have some confidence that I'll be fine. Well, in the case where we don't know, back then we didn't really know how to treat it, cholera could be extremely deadly. And the reason is because the cholera bacteria, when it gets to your intestines, what it does to cause the infection is it produces certain molecules that signal your intestinal lining to essentially reverse their function. Normally, our intestines our cells in our intestine are actively pulling water out of whatever we have been digesting. So pulling water from our gut, from the stuff we've ate and drank, and putting it into our bloodstream. So it's just constantly extracting water for us, and that's really crucial to keep us hydrated. Well, Vibrio cholera will, once you have an infection going, will reverse that. And so then you're taking water from the bloodstream and sending it out the tailpipe, right? So you have an extreme case of diarrhea, and it tends to continue for a few days until the Vibrio sort of just washes itself out in some sense. Your body gets control and kicks it out. And if you survive, you're fine in a week, probably, something like that. So in modern day medicine, we know that, well, we could probably treat with antibiotics, but even if not, it's going to be self-limiting. So as long as we keep a person hydrated and give them care, they're going to be okay in almost all circumstances. So today, it's not very deadly when we have access to IVs, to hydration salts. Just simply having Gatorade and knowing that that's what you needed during such an event would make it almost non-lethal, right? So today we're, it's not such a big deal. But back then, you got sick, that started happening, and dehydration is such a dangerous thing, and the speed at which you're dehydrating in that scenario is like incredible in an awful sort of way. People would die within hours, right? You'd be fine, living and happy in the morning, and then half your family dies by evening. Like, that's going to be terrifying, right? So this was, this plague, as they would know it, was a seriously awful scenario. And especially if they didn't know, how it was transmitted. There was all sorts of ideas. Maybe it's this, the streets back then, there was going to be a lot of sewage around, which certainly is not a good thing. But they just thought that the aroma, this miasma is what they called it, was perhaps the issue. And so as Jon Snow and others were mapping this, what they were kind of showing is, well, it doesn't matter if this is the rich area that's a little cleaner, or the poor area that's a lot more dirty. Everyone would say this is full of miasma or whatever. It didn't matter. It was just around in this area. Here's another plot that kind of gives vertical bars to show it. So absolutely terrifying scenario. And what we see here is the blue flags are different well pumps. So that have probably hand-dug wells, maybe 30 feet deep, something like that, to just get some groundwater. Not the best source of drinking water, as we'll see, but it's something. And so, you can see how what they've done here is they took this map and just took this bar here and just put a vertical bar in place of it to show, kind of show it a little bit vertically. And if you take a look, what they noticed was right here, there's a blue flag for the Broad Street pump. So as soon as they recognized, well, hey, it seems like this is all centered around this particular water source, let's remove the pump handle so people can't get water from there anymore. And that immediately stopped the epidemic. So there was like maybe somebody who had just drank it that day and got sick the next day or something. Still a couple more illnesses, but it was very quickly put an end to the epidemic. And the reason, another reason that they were thinking about this is apparently Jon Snow had some sort of a microscope and was looking at the water, and there's some conjecture that he probably didn't have a microscope that was strong enough to really see the Vibrio cells, but he was seeing some organisms floating around in there and was thinking maybe these are what's causing it. So he was on the right track, apparently, even if he was unable to identify the actual bacteria. And so the confluence of those things, this is the first time we mapped a disease outbreak to enable us to take some action to correct it and fix it, right? So that's what epidemiology is inherently about, although it's maybe gone to a lot more than that these days. Okay, so what happened at that well? It turns out there was an infant, again, their biology is a little bit different, who had an ongoing Vibrio infection. Now, because the biology of an infant is a little bit different, intestines and all are still developing, the infection was not as bad. It was not so lethal to the infant. Apparently was still able to keep hydrated, I suppose, and was just carrying the infection, an active infection, for a week or two. And it turns out that this infant apparently had traveled, the parents had brought it from some other location. It had picked up cholera from there, and then they moved into here, or returned, I think. And it turns out their latrine system basically just dumped the waste essentially to the ground next to the well. So it was seeping into the well, and there was a direct source of cholera, Vibrio cholera, into this well water that this location, all the people in this location were using. So very much a fecal-oral route of transmission here in a very terrible way. So that's kind of the essence of the ghost map story. And ghost map because they mapped, the ghosts, right? The people who had died. So if you ever do visit London, maybe I will one day. I have not, but apparently you can visit the Broad Street pump well, and I think they put back the handle on so you can see what it was like. But of course, it's kind of a historic landmark. It's not functional at this point. Okay, anybody ever seen that or heard anything about that? Okay, so bit of history there. Kind of reminds us pretty clearly why we want to disinfect our water, and kind of ties in a lot of those pieces of, well, what are these diseases? How much does it take to get us sick? Where does all that come from? So to disinfection then. We have a few technologies that we can use. You've all heard of chlorine, probably all heard of ultraviolet light as a disinfectant, probably heard of sunlight in that context as well, so we'll talk about that. We can also have chlorine dioxide, which is another reactive chlorine species, a bit different, but similar in effect. Ozone, so O3, which is a natural oxidant, can be used. And sometimes that's pretty good against these cells that tend to form the cysts and protect themselves against chlorine. So sometimes we'll use ozone for that. And then the last one I have here, we sometimes use advanced oxidation processes, which is typically like taking UV plus one of these oxidants, like hydrogen peroxide, blasting it in such a way that we create really highly reactive radicals. And this is not so much disinfection, although it would certainly achieve disinfection, but more so to destroy, let's say, pharmaceutical compounds. We'll say so, destroy organic molecules and some stuff like that. So if we had maybe some pesticides that we were worried about might be in our water, we might apply an advanced oxidation process to get rid of those, or antibiotics or something like that. So that would be a bit more intense. I'm lumping it in here with disinfection technologies because it's kind of related and could achieve the same outcomes, but we actually would design it a little differently based on the chemical side of things. Okay, so let's talk about chlorine first. We've discussed chlorine a bit in the context of equilibrium chemistry. Mostly I was trying to give you some of that background, give you some time to warm up with that so that we could apply it here essentially. So it turns out that when we add chlorine gas, we can add chlorine as chlorine gas, or we can add it as something like sodium hypochlorite, which is what you'll find in household bleach. So let's take for a moment chlorine gas. If we react that, with water, we will get some of it will go into the water will split and say we have an HOCl. So we'll get a chlorine and part of the water, plus the rest of that water is the H plus that came off, plus Cl minus. So half of this chlorine molecule, the Cl2, forms this HOCl, and this is our reactant. Right here, that's we would call this free chlorine. The Cl minus here, that's chloride. That doesn't really react with much, right? We get that when we take table salt. And table salt doesn't really react much, right? It's NaCl, we get Cl minus. The deal here from a chemical perspective is one of these chlorines would really like to take some more electrons, and one of them is already happy and has all the electrons at once, okay? So the Cl minus has all the electrons at once. This HOCl would really like to oxidize something. Oxidize meaning like taking away the electrons, typically adding an oxygen group or something in place. We oxidize things when we burn them, right, in the atmosphere. If we have oxygen in the atmosphere and we light a fire, we are oxidizing something with that chemical reaction. The other way would be, so this is one way we'll get the HOCl. Another way is if we added, let's say, NaOCl. If we put that in water, the sodium will come out and we'll be left with OCl minus and Na plus. Now, in either case, we end up with both HOCl and OCl minus because they have some equilibrium equation, equilibrium reaction between them. That's simply that a proton, the H plus, can hop on or hop off, right? This is just an acid-base chemistry sort of thing. That's just what happens. So it turns out that HOCl is the stronger form. And I'll say that the OCl minus and the HOCl are free chlorine, right? The combination of the two is free chlorine. And we're always going to have the combination of the two, really. So it turns out, like I said, the HOCl is stronger. So we want to design our system based on HOCl. So we will design disinfection based on HOCl. It's like 8 to 10 times stronger of a disinfectant than OCl minus. So it actually makes a pretty big difference, and it's fairly important that we use the right one for our purpose. Now, if we look at the equilibrium equation, the way to force it over towards HOCl is to add a little bit of acidity, because as soon as we're adding more of the H plus to our solution, that tends to push the balance of the equation to the left, right? If we add a lot of reactants, we make more products, right, in this kind of equilibrium equation. So that means that in slightly acidic conditions, we'll have plenty of HOCl. And the reason for that is we've seen it before, but the equilibrium constant is 10 to the negative 7.5-ish. Or we could write that pKa is 7.54. That means we'll have an equal amount of HOCl and OCl minus at pH 7.5. So at a slightly basic condition, close to neutral, they're equal. Anything below that is going to give us what we wanted. So disinfecting at pH 5 or 6 range is pretty typical. That makes good use of our chlorine. It doesn't take a whole lot of acid to change the chemistry that way, or to change it back when we ship it out through the distribution system. Okay, so that means when we do solve chlorine problems, we will often have to consider this relationship. So let's take a minute to practice. We have a condition where we say 15 milligrams of HOCl is added to a potable water supply, I guess, for disinfection. Potable is a fancy word for saying drinking, or intended for drinking. Okay, and the final measured pH is 7. What percent of HOCl is not dissociated? And it says assume the temperature is 25 Celsius. That just is there to tell us we could look up or calculate some value for our equilibrium constant. I'm just going to say this will be 10 to the minus 7.54. So take a few minutes, work on that, work with each other if you like. so I think you all had a shot at it. Maybe wrapping up some calculations here. So I'm going to walk you through it. There's actually a little bit of a red herring, so to speak, in this problem, a distraction. We're given some mass concentration of HOCl. So you probably are immediately thinking, well, hopefully one thought you had was, well, we have this mass concentration, we'll probably have to go to molar concentration so we can use this equilibrium and figure stuff out. But actually, we didn't have to even dig into that because we were asked about the proportion. Now, if you were asked what amount of it is in HOCl, then yeah, we'd have to do that conversion and look into it in that manner. But because we're just looking at the percentage, that actually doesn't matter how much is there, just some percentage of it will be one way or the other. So because the percentage doesn't care about how much is there, it's just the percentage, we can actually just set that aside and deal with it if we needed to, which in this case we don't really. So we can start by, first of all, defining, okay, here's our equilibrium reaction. Then that means we have an equation with Ka. Ka is equal to the products over the reactants multiplied together. So H plus times OCl minus divided by HOCl. Then we have the actual question itself is asking us what percent is not dissociated, meaning what percent is left in the HOCl form. So when we say dissociated or non-dissociated, this is the dissociation reaction, right? That's our dissociation. So if it's not dissociated, that means it's just HOCl. So to be clear, that's what the question is asking for. What proportion of this stuff, of the total chlorine, is still in HOCl form? So we can write that as HOCl divided by the total amount of chlorine, which is OCl minus plus HOCl. And then multiply that by 100% to get a percentage. Now, we've done this before, so I'm just going to remind you what we can do here is divide, to simplify this, to divide the top and the bottom by HOCl, and we'll be left with a fraction that's 1 over 1 plus OCl minus divided by HOCl. Now that we have these in terms of like a proportion, a ratio of one to the other, it becomes a little easier to substitute in this equation here because we can also get that in a similar proportion. And if you stop and think about it a moment outside of chemistry altogether, if I were to tell you I've got, a bunch of M&Ms and there's 3 times as many red ones as blue ones and they're all either red or blue, you could tell me what percentage of those are red. It'll take a little bit of math. This is actually that math. That's all we're doing here. I gave you a proportion of one to the other, and you can figure out, what that is in terms of a percentage if you know that proportion, right? So you could say it's going to be the red M&Ms divided by the red plus blue, or and then you think, oh, I need to know the amount of red and I need to know the amount of blue. But if you know the ratio between them, you can solve that problem, right? Intuitively, you know that already. So that's just what we're doing here, if that helps at all, to see it that way. So then to get the ratio, this equation tells us that, given some pH. So we can rearrange this to say OCl minus, we could do red to blue or blue to red, right? Either way, we can work with it because we can recognize that we can invert it if we needed to. So the OCl minus divided by the HOCl, I'm just going to divide both sides by H plus. So that'll give us Ka over H plus. Okay, so then we can substitute that in here and say 1 over, I'll say 1 plus the Ka, 10 to the negative 7.54, divided by the pH, which was, pH was 7, so that's 10 to the minus 7 for the H plus concentration. And this should come out to be something that's a little bit over 50% because we're slightly more acidic. So anybody have that number for me? Multiply by 100. Anybody get this without the help? 77%. That sounds right to me. All right, does that make sense? Okay, so it's that, primarily it was just some algebra that we needed that looks like chemistry. Okay. Now, if we did need the amount, what amount of HOCl do we have here? Then we would apply this, convert that to moles so that we can convert it properly, and about 77% of that on a molar basis is HOCl, and we could find that then as needed. Okay, so then a bit more about chlorination. One of the things that we might realize is, well, if we're having trouble chlorinating, let's say for a difficult pathogen like crypto, and we want to get rid of the crypto, why not just chlorinate extra? Like, why not just blast it? Well, there's always the obvious cost reason, right? We don't want to spend more money on chemicals than we need. But there's also a challenge of accidentally forming something called disinfection byproducts. So when we have a water source of some sort, there's going to be some natural organic matter in that water. That's just going to be a given, whether it's groundwater and there's a bit of organic matter, organic molecules from the soil, whether it's leaves decaying in the rivers, providing this natural organic matter stuff. It's a lot like having tea in your, tea leaves in hot water, right? There's going to be a lot of organic molecules coming off into your solution. And, it might not be a huge amount in this scenario of like a nice clean river, but there's going to be some. Even if we can't see them in the visible range, they'll be there. So these are going to be some mixture of random organic molecules. There may be some commonality between them, but it's an assortment, a big, wide assortment, all sorts of stuff. And generally, they're not particularly harmful. They're pretty low concentration. There's nothing really that's a terrible thing about them by themselves. However, if we use a bunch of chlorine or bromine or something, we could add these halogen groups, which tend to make molecules a bit more toxic if we halogenate the molecules. So, for example, just a bit of organic chemistry here for you. When we have some big molecule, just kind of the rest of the molecule, people often write it as R. I'm just going to call that the rest of the molecule, right? And so if we have a molecule that has some methane group, methane is just CH4, but if it is attached to something else, we'll just call it a methyl group. That's what we say for organic chemistry. We got the rest of the molecule and then the methane group, right? So then we add a bunch of chlorine and we chlorinate it. So then we get a same methyl group here, but now instead of the hydrogen, we've popped it off and inserted a chloride. First of all, we notice hydrogen is pretty light. It's a small, it's just 1 gram per mole. Chlorine is a much larger one, so we're changing it, the properties pretty significantly. What we've just done is we've created a trihalomethane. So it was a methane group, now it's trihalomethane. So halogens meaning like the chloride, fluoride, bromide, all that. So these tend to be toxic. And that would be toxic if it was just a methane with 3 chlorines added. It would be toxic if there was some other part of the molecule and then it has a methyl group on the end and then that's now halogenated. So trihalomethanes are a big one. Haloacetic acids are another one. There are several classes of these types of molecules that can be a pretty significant concern for toxicity and carcinogenicity, if I could say it. So the deal is we don't want that, right? So we want to be careful not to over-chlorinate or perhaps remove some of this organic matter to just lower the dose that way. So there are some considerations. One thing that could help is to use this lower amount of chlorine but give it a longer amount of time. We'll see when we get to the Flint water crisis that that was one of their issues. They didn't have a reactor quite big enough, so they added a lot of chlorine. They ended up with a lot of halogenated byproducts, disinfection byproducts, and to the point where they were getting in trouble for that. So that's one of the other considerations here, disinfection byproducts. And that kind of ties in pretty well with when we're designing a chlorine system, or really any disinfection system, we have this concept called contact time. And you'll probably be pretty familiar with this if you've ever used bleach to clean something. And if you are trying to clean up a pretty dirty stain or something, you kind of know or have been taught that you ought to spray it on there, or maybe the label tells you, spray it on there, and if it's a particularly difficult one, you leave it there for a little while, right? You just leave the bleach sitting there. Maybe you pour a lot of it, get it high concentrated, and you give it time. So it turns out that these chlorination reactions, they take some time, and they depend on how much chlorine you have, right? So if you've got a lot of chlorine, a lot of time, you'll get a lot of bleaching, right? You could try it on your clothes. If you like the clothes, don't try it on those, right? So you would see this, right? And you would also recognize if you were, for some reason, cleaning with bleach and you liked your clothes and you got some on you, you'd probably try to wash it off as soon as you can, right? To avoid ruining your clothes. So the dosage is going to be a combination of the concentration and the time we give it. So it should be pretty intuitive there. We would call this the CT concept, or the contact time concept. Functionally, and on mass balance, this is an equation that really was put forward back in, I think, 1908, called the Chick-Watson. We call it Chick-Watson kinetics. There was a couple different researchers kind of came to the same conclusion here, that basically when we're disinfecting something, if N is our amount of bacteria or viruses or whatever, a reaction where we're destroying them will generally be a first order reaction with respect to those bacteria, right? How many we destroy will depend on them. So that's a first order with respect to the number of pathogens. However, we also have a dependence on the amount of disinfectant we have. So concentration of disinfectant. So this can look pretty scary if we start to think, well, maybe our amount of chlorine is changing with time and the number of pathogens. How are we ever going to integrate that properly? Well, fortunately, we can often assume our concentration of our disinfectant is constant. So if we apply some amount of chlorine, we assume that we've kind of got that same amount of chlorine, at least for the 10 minutes we're doing this contact or something. Might be a little trickier with ozone, but in that case, we'd probably be bubbling it and resupplying it over time, so we would still have some sort of effective concentration. Now, there is a little factor here, the N. That's to account for the fact that maybe we have some dilution issue where maybe not all the chlorine is well mixed. Some of the reactor doesn't have as much chlorine, or maybe the ozone, the way we're approaching it, is only getting to 3/4 of the reactor or something. For an ideal reactor, we assume that's 1. So typically what we will do is just treat this like that's a 1. We've got the 1 there. And then we have this equation. If we assume C is constant, it just looks exactly like any of the other decay reactions we've used, right? And we can put it into a CSTR, or we could put it into a plug flow reactor. This is just a generic reaction term where the rate of change of N depends on N to the 1 power, and then there's some constants involved, right? The only difference is we also have the C as part of the constants. So we could even combine these two constants and say, well, let's get a total K for the entire system that's K times the concentration. That would act like the constants we are used to using in a per time unit, right? Now, the actual K in here that's individual, we would call that a coefficient of specific lethality. That's specific to the chlorine or whatever disinfectant we're using and the microorganism. So some organisms are more resistant than others. So we actually have to know pretty good details about, okay, how fast does ozone kill E. coli? How fast does ozone kill norovirus? And based on what we're trying to design for, that K would come into here. Okay, so given that, we can have this coefficient of specific lethality that has units of 1 over concentration. So that's going to account for the concentration here of the disinfectant, and per time, in order for the total units to come out to be a change in number per time, number concentration per time. Okay, so overall, it's pretty much the same thing as what we've been doing all semester now, but there's the caveat here that we are also accounting for the concentration. All right? Okay, so just a quick look at this. This is some research I did as a grad student where we were using a particular photosensitized reactive oxygen species called singlet oxygen, and it was killing some virus, attacking this MS2 bacteriophage virus. It's a virus that infects E. coli. It's pretty convenient to work with. And basically what we're showing here is the more of this stuff we were producing, maybe we added more light, maybe we added more of this material that was creating it, the faster the viruses were dying. So if we had a lot of it, the viruses were dying so fast that we had a 5 log removal or more in like 2 minutes, right? But on the flip side, if we had almost none of it, we really weren't having much destruction at all. And if we ignore this one because it's kind of a weird case, I could describe that more, most of these will look pretty linear because this is that first order dependence. Then we're ignoring the one that has something weird happening that's not so first order, okay? But most of these are going to be approximately first order with respect to the amount of viruses that are there, given some constant concentration of this disinfectant. Okay, so I'm going to pick up here next time. What we'll take a look at is some real data for poliovirus disinfection to back calculate some of the K from the data. Okay, so we'll pick up here on Thursday, and I'll see you guys then.